Okay, this is Dr. Brown. I'm going to be putting together a video on how to integrate rational functions using partial fractions. Now give me a second to get the ink color to be correct and to get the pen on. So as I said, we're going to integrate rational functions, which can be written as f of x equal some numerator polynomial divided by some denominator polynomial. You'll recall that earlier today we looked at an example of a rational function and showed that it could be written as 2 over x plus 1 plus 3 over x minus 3. You can confirm that by combining the two partial fractions into 2x minus 6 plus 3x plus 3 divided by x squared minus 2x minus 3, and you can see that this becomes 5x minus 3, and is exactly what we started with. And we notice that if we could decompose the rational function into two partial fractions, that we could easily integrate the partial fractions into 2 ln of the absolute value of x plus 1 plus 3 ln of the absolute value of x minus 3 plus a constant. Now, on the next sheet, I'm going to briefly show how you can do partial fractions using a cover-up method. I don't think you'll see it called a cover-up method in the book, but this is a method I learned a long time ago, and I think it's used in a lot of different places, but maybe they don't call it cover-up. Anyway, let's say you can take a function of x equal a numerator divided by the denominator, and suppose you can write that as a numerator divided by the factors of the denominator, x minus x1, x minus x2, all the way down to x minus x sub n, if you had, n factors. And that could be written as a1 divided by x minus x1 plus a2 divided by x minus x2, all the way down to a sub n over x minus x sub n. Now we assume that x1, x2 through x sub n are distinct and not equal. That is, they're all different factors, and that n of x is at least one order less than the order of the denominator. And if that is so, we can show that a1 can be written as the numerator divided by x minus x1, but you cover it up and evaluate the rest of the function at x equal x1. And a2 can be written as n of x divided by x minus x1. Don't cover it up, but cover up x minus x2 all the way down to x minus x sub n. Evaluate at x equal x2. And in general, if you have n distinct factors, a sub n, of course, would be equal to n sub x divided by x minus x1, x minus x2, and cover up the x minus x sub n, and evaluate it at x equal x sub n. And then you can show that the integral of f of x dx, which can be broken up into your partial fractions, can be written as a1 ln of the absolute value of x minus x1 plus a2 ln of the absolute value of x minus x2 all the way down to a sub n ln of the absolute value of x minus x sub n. And there you have the entire thing integrated. Now, just to illustrate what we did earlier this afternoon, the particular example we looked at, f 5x minus 3 divided by x squared minus 2x minus 3 equals 5x minus 3 divided by x minus 3, x plus 1, and we believe that can be written as a over x minus 3 plus b over x plus 1. And a can be figured out by evaluating 5x minus 3 over x minus 3, cover it up, and evaluate the remainder of this with the x minus 3 covered up at x equal 3, and that equals 15 minus 3 divided by 3 plus 1 equals 12 over 4 equals 3. B equals 5x minus 3 divided by x minus 3, cover up x plus 1, and evaluate it at x equal minus 1, and you will get minus 5 minus 3 over minus 1 minus 3 equal minus 8 over minus 4 is equal to 2. That means that the integral of 5x minus 3 divided by x squared minus 2x minus 3 can be written as the integral of a, which is 3 over x minus 3 dx. By the way, I should have a dx there too, plus the integral of 2 over x plus 1 dx, and that equals 3 ln of the absolute value of x minus 3 plus 2 ln of the absolute value of x plus 1 plus a constant. Now, I want to illustrate something that Heather was alluding to. Suppose the numerator is 1 or more degrees greater than the degree of case, you need to do long division of the rational function so that you can get a remainder that will have a numerator that's at least one less than the denominator. So you probably recall how to do a long division. We'll take x squared minus 2x minus 3 divided into 2x cubed minus 4x minus x minus 3. And you can see dividing x squared into 2x cubed gives you 2x. Multiplying 2x times the divisor, we get 2x cubed minus 4x squared minus 6x. And now we subtract 2x cubed minus 2x cubed is 0. Minus 4x squared minus 4x squared is 0. And then subtracting, we get minus x minus 6x is 5x. Bring down your minus 3, and we have a remainder of 5x minus 3. So the original rational function is equal to 2x plus the remainder over the divisor. And now you can see that we can integrate this entire thing by integrating 2x, which is x squared, and we already knew that the integral of the 5x minus 3 over x squared minus 2x minus 3 is what we have down here. So now we have the entire integral. And I'm glad that Heather mentioned that because I think it's worthwhile knowing, although I'm sure you all know how to use long division. Now let's work about 4 problems here. And the first problem is shown here, number 1. We want to do the antiderivative 4x plus 23 over x squared plus 9x plus 20. And before we get started, I'd like to remind you that ln of x to the n is equal to n ln of x, which means that nln of x is equal to ln of x to the n. And also ln of, say, y over x is equal to ln of y minus ln of x. So if ln of y minus ln of x you have in your answer, you can write that as ln of the quotient of y and x. You'll see that some of these answers you first get, you might have to utilize some of these logarithmic properties. So now let's start off and write our 4x plus 23 divided by x squared plus 9x plus 20 is equal to 4x plus 23 over x plus 4, x plus 5. These are the factors. And we should be able to write this as a over x plus 4 plus b over x plus 5. And a can be written as 4x plus 23 divided by x plus 4, and cover it up, x plus 5, don't cover it up, evaluated at x equal minus 4, and you'll see that this is minus 16 plus 23 divided by minus 4 plus 5 equals 7. So A is equal to 7. The B is equal to 4x plus 23 divided by x plus 4, x plus 5, cover up the x plus 5 and evaluate it at x equal minus 5. We get minus 20 plus 23 divided by minus 5 plus 4 equals 3 over minus 1 equal minus 3. So the integral of 4x plus 23 divided by x squared plus 9x plus 20 dx is equal to the integral of 7 over x plus 4 dx minus the integral of 3 over x plus 5 dx equals 7 ln of the absolute value of x plus 4 minus 3 ln of the absolute value of x plus 5 plus a constant. Now, using the properties of logarithms, we can see that's ln of x plus 4, absolute value of that to the 7th power, minus 3, minus ln of the absolute value of x plus 5 to the 3rd power, plus a constant, which can be written using the quotient property as ln of x plus 4 divided by x plus 4 absolute value to the 7th power divided by absolute value of x plus 5 to the 3rd power plus a constant. And that is answer D. The next problem is one in which we can take x plus 9 divided by x squared plus 5x and write that as x plus 9 over x times x plus 5. Those are the factors. We should write that as a over x plus b over x plus 5. And a can be written as x plus 9 over x, cover it up, times x plus 5, evaluated at x equals 0, and you get 9 over 5. And you get that b is equal to x plus 9 divided by x, x plus 5, cover it up, evaluated at x equal minus 5, and you get 4 over minus 5 equal minus 4/5. So we can write that the integral of x plus 9 divided by x squared plus 5x dx is equal to the integral of 9/5 times 1 over x dx minus the integral of 4/5 times 1 over x plus 5 dx, which is equal to 9/5 ln of x minus 4/5 ln of x plus 5. That's the absolute value of x, by the way. Plus a constant. And we can take a fifth factor out and write this as 1/5 ln of 9 ln of x minus 4 ln of x plus 5 plus a constant. And you see we can write that as 1/5 ln of x to the 9th divided by x plus 5 to the 4th power. The absolute value of all of that plus a constant. Number 3 is a third order rational function. We can write 40 over x cubed minus 4x as 40 over x plus 2, x minus 2 equals a over x plus b over x plus 2 plus c over x minus 2. And now we have 3 constants to determine. A is equal to, by the way, this is 40. A is equal to 40 over x, cover that up, x plus 2, x minus 2, evaluated x equals 0, gives you 40 over minus 4 equal minus 10. B is equal to 40 over x, x plus 2, x minus 2, cover up the x plus 2, evaluate at x equal minus 2, and we get 40 over plus 8 equal 5, and then finally C is equal to 40 over x, x plus 2, x minus 2, cover it up, evaluated at x equal plus 2, and you get 40 over 8 equals 5. So the integral of 40 over x cubed minus 4x dx equals the integral of minus 10 over x dx plus the integral of 5 over x plus 2 dx plus the integral of 5 over x minus 2 dx. And this is equal to minus 10 ln of x plus 5 ln of the absolute value of x plus 2 plus 5 ln the absolute value of x minus 2 plus a constant, which is equal to b. And finally, the last problem we're going to look at is a definite integral. We need to be able to write 8 over x squared minus 16 as 8 over x minus 4 times x plus 4 equals a over x minus 4 plus b over x plus 4 And A can be calculated by writing A over x minus 4, cover it up, x plus 4 at x equals 4, which is 8 over 8 equals 1. Similarly, B is equal to 8 over x minus 4, cover up the x plus 4, and evaluate it at x equal minus 4, and you get 8 over minus 8 equal minus 1. So we have the integral from 5 to 10 of 8 over x squared minus 16 dx equals the integral from 5 to 10 of 1 over x minus 4 minus 1 over x plus 4 dx, and that equals ln of x minus 4 minus ln of x plus 4. And we want to evaluate it between 5 and 10. And you could go ahead and evaluate that or write it as ln of x minus 4 over x plus 4, evaluated at 5 and 10, and you get ln of 6/14 minus ln of 1/9, and plugging into that you get 1.350 as the answer. Plug it into your calculator. So that is what we're going to do with partial fractions.